I want to talk to you about an experiment that has puzzled, fascinated, and troubled physicists for nearly a century. It is an experiment so simple in its setup that you could, in principle, perform it in a modest laboratory, and yet so profound in its implications that it forces us to reconsider everything we thought we knew about the nature of reality. This is the double-slit experiment, and Richard Feynman once said that it contains the only mystery of quantum mechanics. I would go even further. I would say it contains the central mystery of nature itself, the place where our classical intuitions break down completely, and we must face the strange, beautiful, and deeply counterintuitive character of the quantum world. Let me begin by telling you how I first encountered this puzzle, though not in its modern quantum form. When I was a student at the University of Copenhagen in the early years of the 20th century, we learned about Thomas Young's famous experiment from 1801, which had settled once and for all, or so it seemed, the question of whether light was a wave or a stream of particles. Young had taken a beam of light and passed it through two narrow slits cut into an opaque screen. On a second screen placed behind the first, he observed not two bright bands as you might expect if light were particles passing through one slit or the other, but rather a pattern of many alternating bright and dark bands, an interference pattern of exactly the sort you see when water waves pass through two openings and overlap on the other side. This interference pattern proved that light was a wave. When a wave passes through two slits, each slit becomes a source of circular waves spreading outward. Where the crests of waves from both slits arrive together, they reinforce each other and create bright bands. Where a crest from one slit meets a trough from the other, they cancel out and create dark bands. This is constructive and destructive interference, and it is the unmistakable signature of wave behavior. Newton had believed light was made of particles, corpuscles as he called them, but Young's experiment seemed to prove Newton wrong and established the wave theory of light beyond doubt. Of course, the story did not end there, as stories in physics rarely do. In 1905, the same year he published his theory of special relativity, Albert Einstein proposed that light also behaves as if it is made of discrete particles, quanta of energy that we now call photons. He did this to explain the photoelectric effect, the way light can knock electrons out of metal surfaces. The energy of the ejected electrons depends on the frequency of the light, not its intensity, which makes perfect sense if light comes in particle-like packets, but makes no sense at all if light is purely a wave. Einstein received the Nobel Prize for this work, not for relativity, which tells you how important and convincing it was. So now we had a paradox. Light behaves like a wave in Young's double-slit experiment, showing interference patterns. But light also behaves like particles in the photoelectric effect, transferring energy in discrete chunks. How can light be both wave and particle? This wave-particle duality, as we came to call it, was deeply troubling. It seemed to violate the law of non-contradiction, one of the most basic principles of logic. A thing cannot be both A and not A at the same time. But then the situation became even more puzzling. In the 1920s, Louis de Broglie proposed that if light, which everyone had thought was a wave, could behave like a particle, then perhaps matter, which everyone thought was made of particles, could behave like a wave. He suggested that electrons, which J.J. Thomson had discovered and which everyone pictured as tiny charged balls, should also exhibit wave properties under the right circumstances. The wavelength associated with an electron, de Broglie said, would be inversely proportional to its momentum. This was a bold proposal, and it was quickly confirmed by experiment. Clinton Davison and Lester Germer in the United States, and independently George Paget Thomson, the son of J.J. Thomson, in England, fired beams of electrons at crystals and observed diffraction patterns exactly like those produced by X-rays, which were known to be waves. The electrons were behaving like waves. Matter itself had wave properties. This brings us to the heart of the most confusing experiment ever, the version of the double-slit experiment performed not with light but with electrons. Imagine we have a source that emits electrons, an electron gun if you like. We place a barrier in front of it with two narrow slits cut into it. Behind this barrier, we place a screen that lights up wherever an electron hits it, perhaps a phosphorescent screen or a photographic plate that records each impact as a tiny dot. Now, if electrons were simply particles, little balls following definite trajectories, we would expect to see two bands on the screen, one behind each slit. Some electrons would go through the left slit and hit the screen in a cluster behind it. Some would go through the right slit and hit the screen behind that one. We might see some spreading due to diffraction at the edges of the slits, but basically two bright bands. But this is not what we observe. Instead, we see an interference pattern, multiple bands of bright and dark regions, exactly like the pattern produced by waves. The electrons are interfering with each other, creating regions where they preferentially arrive and regions they seem to avoid. This proves that electrons, like light, have wave properties. The matter wave associated with each electron passes through both slits, and the waves from the two slits interfere with each other. Now, you might think that this interference occurs because electrons are bumping into each other as they travel, like water molecules in a wave might interact. So let us modify the experiment. Let us turn down the intensity of our electron source so low that only one electron is emitted at a time. We send electrons through the apparatus one by one, with enough time between them that each electron completes its journey and hits the screen before the next one is emitted. There is no possibility of electrons interacting with each other. What do we observe? Each individual electron hits the screen at a single point, making a tiny flash or dot. It behaves like a particle when it arrives. But here is the astonishing thing. As we repeat the experiment many times, sending thousands of individual electrons through the apparatus one at a time, the dots gradually build up the same interference pattern we saw before. The alternating bright and dark bands emerge from the accumulated impacts of individual particles. This is where the confusion and the mystery really begin. Each electron arrives as a particle, hitting one specific location on the screen. But the pattern built up by many electrons is a wave interference pattern. How can this be? Each electron goes through the apparatus alone, so it cannot be interfering with other electrons. Yet the interference pattern appears anyway. The only conclusion we can draw is that each individual electron somehow passes through both slits simultaneously and interferes with itself. The electron, even though it is a single particle, behaves like a wave that splits at the two slits and then recombines to create the interference pattern. This is not merely strange or counterintuitive. It seems to violate our basic notions of what it means for something to be at a particular location. Now, you might object that this is unsatisfactory. Perhaps the electron does go through one slit or the other, and the interference pattern arises from some subtle effect we have not understood. So let us perform another modification to the experiment. Let us place detectors at each slit that can tell us which slit each electron passes through. We can use weak light to observe the electrons, or any other gentle method that in principle allows us to determine the electron's path without significantly disturbing it. What happens when we add these detectors? The result is shocking. The interference pattern disappears completely. When we monitor which slit each electron goes through, we get two simple bands on the screen, exactly what we would expect for particles going through one slit or the other. The wave interference is gone. Let me emphasize this, because it is crucial. When we do not observe which slit the electron passes through, we get an interference pattern that proves the electron behaves like a wave going through both slits. When we do observe which slit the electron passes through, we get two bands that prove the electron behaves like a particle going through one slit or the other. The very act of observation changes the outcome of the experiment. This is not because our detectors are clumsy and disturb the electrons mechanically. Even the most gentle possible observation, one that transfers minimal energy and momentum, still destroys the interference pattern. The effect is fundamental, not technical. The electron seems to know whether we are watching it, and it changes its behavior accordingly. How can we possibly understand this? In classical physics, we assume that objects have definite properties independent of whether we observe them. A ball rolling down a hill follows a definite trajectory whether anyone is watching or not. The moon is there in the sky even when no one is looking at it, as Einstein liked to say. But the double-slit experiment with electrons seems to violate this assumption at the quantum level. The explanation that emerged from quantum mechanics, the interpretation I worked out through many long discussions with Werner Heisenberg, Wolfgang Pauli, and others in Copenhagen, is this: before we measure which slit the electron goes through, the electron does not have a definite path. It is not the case that the electron really went through the left slit, or the right slit, and we simply do not know which. Rather, the electron is in a quantum superposition of going through both slits simultaneously. This superposition is not just a mathematical convenience or a statement about our knowledge. It is a description of the physical state of the electron. The electron is described by a wave function, which in this case has components corresponding to the electron passing through the left slit and components corresponding to it passing through the right slit. Both components are real and present, and they interfere with each other, creating the interference pattern we observe. The electron is genuinely in both places at once, or more precisely, it is in a state that cannot be described as being definitely in one place or definitely in the other. When we place detectors at the slits and observe which path the electron takes, we perform a measurement that forces the electron to choose one path or the other. The wave function collapses, as we say. The superposition of both paths reduces to a definite state where the electron has gone through one particular slit. Once this happens, there is no interference, because interference requires the superposition of both paths. This is what I came to call complementarity. The wave and particle properties of the electron are complementary aspects of its nature. We can design our experiment to reveal the wave aspect, by not measuring which slit the electron goes through, and then we see interference. Or we can design our experiment to reveal the particle aspect, by measuring which slit it goes through, and then we see two bands. But we cannot see both aspects simultaneously. They are mutually exclusive experimental situations. The electron is neither purely a wave nor purely a particle. It is something for which we have no direct classical analog, something that exhibits wave-like behavior in some experimental contexts and particle-like behavior in others. Asking what the electron really is, independent of how we measure it, is not a meaningful question in quantum mechanics. The properties we observe depend on the experimental arrangement we choose. I know this sounds almost mystical, as if we are giving consciousness or observation some magical power over reality. But this is a misunderstanding. The key is not consciousness but physical interaction. When we place a detector at a slit to determine which path the electron takes, we are creating a physical interaction between the electron and the detector. This interaction entangles the quantum states of the electron and the detector in a way that destroys the superposition. It is not that a conscious mind collapses the wave function by looking at the detector. It is that the physical process of detection, the irreversible recording of information about the electron's path, fundamentally changes the quantum state. Let me give you a variant of the double-slit experiment that makes the situation even stranger, if that is possible. This is the delayed choice experiment, first proposed by John Wheeler. Imagine we set up the double-slit apparatus as before, but we place a movable second barrier between the slits and the screen. This barrier can either be absent, allowing both paths to reach the screen and interfere, or it can be present with two detectors that determine which slit the electron came from before it hits the screen. Now, here is the twist. We wait until after the electron has passed through the slits before we decide whether to insert this second barrier with detectors or leave it absent. We make this choice randomly, perhaps triggered by a quantum random number generator, after the electron has committed to its path, so to speak. If the electron really went through one slit or the other when it passed the first barrier, then our later choice about whether to detect it should not matter. But in fact, it does matter. If we choose not to detect which slit it came from, we see interference. If we choose to detect which slit it came from, the interference disappears. It is as if the electron retroactively adjusts its past behavior based on our future choice about how to measure it. Of course, this is not really what is happening. What is happening is that the entire experimental setup, including our choice of whether to measure the path, determines the quantum state of the system, and thus what we observe. We cannot separate the electron's behavior from the measurement context. The electron does not have a definite path that exists independent of our choice about how to complete the experiment. These results have been confirmed in countless experiments over the decades, with electrons, photons, atoms, and even larger molecules. The double-slit experiment with its strange wave-particle duality and the role of measurement in determining outcomes is not a theoretical speculation or a mathematical curiosity. It is an empirical fact about how nature behaves at the quantum level. But why is this experiment so confusing? I think the confusion arises because we are trying to fit quantum phenomena into classical concepts that simply do not apply. We want to think of the electron as a little ball that must be at some definite location, following some definite trajectory, going through either the left slit or the right slit. We want to maintain the classical picture where objects have properties independent of observation. But nature at the quantum level does not conform to these expectations. The electron is not a classical object made very small. It is a quantum object, and quantum objects obey different rules. They can exist in superpositions of states that would be mutually exclusive for classical objects. They do not have definite values for all their properties simultaneously. Their behavior depends on the entire experimental context, including what measurements we choose to perform. I spent much of my career trying to help physicists understand this, trying to articulate what quantum mechanics is really telling us about nature. I developed the concept of complementarity to explain how wave and particle descriptions are both necessary but mutually exclusive. I emphasized that quantum mechanics is not about describing an objective reality that exists independent of observation, but about predicting the outcomes of measurements in precisely defined experimental situations. Albert Einstein never accepted this view. He felt that physics should describe reality as it is, not merely predict measurement outcomes. He proposed various thought experiments designed to show that quantum mechanics must be incomplete, that there must be some deeper theory with hidden variables that would restore determinism and objectivity. The most famous of these was the EPR paradox, which tried to show that quantum mechanics led to absurd non-local correlations that violated relativity. I remember many long discussions with Einstein, some of them quite heated, though we always maintained mutual respect. I argued that his objections were based on classical prejudices about what physics should be like, assumptions that needed to be abandoned in the quantum domain. Einstein argued that I was giving up too easily on the goal of understanding reality as it truly is. In the end, we agreed to disagree, though I think history and experiment have vindicated the quantum view. Decades after these debates, physicists developed experimental tests of Bell's inequalities that could distinguish between quantum mechanics and any theory based on local hidden variables. These experiments, performed with increasing sophistication from the 1970s onward, have consistently confirmed quantum mechanics and ruled out Einstein's hope for hidden variables. Nature really is non-local in certain respects. The correlations predicted by quantum mechanics, which Einstein thought were absurd, are real. But let me return to the double-slit experiment, because I want to address one more aspect that makes it particularly confusing. When we say the electron passes through both slits simultaneously, we do not mean that half the electron goes through one slit and half through the other, like a wave of water might divide. The electron is indivisible. When it hits the screen, it always arrives as a whole particle, never split into pieces. So in what sense does it go through both slits? The answer is that the wave function, which describes the electron's quantum state, has amplitude at both slits. The wave function is not a physical wave made of some substance. It is a mathematical object, a complex-valued function that encodes probabilities. The square of the wave function's amplitude at any location gives the probability of finding the electron there if we measure its position. Before measurement, the electron is not definitely at any location. It is in a superposition where position is not a property that has a definite value. When the wave function encounters the two slits, it develops amplitude in both paths. These two components of the wave function propagate forward and overlap at the screen, interfering with each other. Where they interfere constructively, the probability of finding the electron is high. Where they interfere destructively, the probability is low. This is why we see the interference pattern build up from many individual electron detections. But when we place detectors at the slits, we entangle the electron state with the detector states. The part of the wave function where the electron goes through the left slit becomes correlated with the detector registering left, and the part where it goes through the right slit becomes correlated with the detector registering right. This entanglement prevents the two parts of the wave function from interfering at the screen, because they are now distinguishable. The system as a whole is in a superposition, but it is a superposition of macroscopically different states that do not interfere. This process, where quantum superpositions are suppressed by interaction with many particle systems like measuring devices, is called decoherence, and it helps explain why we do not see quantum interference effects in everyday macroscopic objects. But even with decoherence, the fundamental strangeness remains. The electron really is in a superposition before we measure it, and measurement really does collapse this superposition in a way that is not described by the usual deterministic evolution of quantum mechanics. The double-slit experiment is confusing because it confronts us with the inadequacy of our classical concepts at the quantum level. We cannot visualize what is happening in a way that satisfies our intuitions developed from everyday experience. We cannot construct a simple picture where the electron is a little ball following a definite path. We can only describe the electron mathematically with a wave function and predict probabilistically what we will observe when we measure. Some people find this unsatisfying. They feel that physics should give us more than mathematical predictions, that it should tell us a story about what is really happening, a story we can visualize and understand in familiar terms. I sympathize with this desire, but I think it asks too much of nature. The quantum world is genuinely different from the classical world, not just in degree but in kind. Our visualizations and intuitions are adapted to the macroscopic world where quantum effects average out. They are not reliable guides to atomic and subatomic reality. The most confusing experiment ever is confusing precisely because it reveals this fundamental strangeness. It shows us that electrons are neither waves nor particles in the classical sense, but something more subtle that exhibits both behaviors depending on how we interrogate it. It shows us that superposition is real, that quantum objects can exist in states that are classically impossible. It shows us that measurement plays a special, irreducible role in quantum mechanics, determining which of many possibilities becomes actual. I have lived with this confusion for my entire career. I have thought about it, discussed it, defended it against critics, and tried to help others understand it. And yet I confess that even now, the double-slit experiment fills me with wonder and a kind of intellectual vertigo. Every time I think about an electron passing through both slits at once, interfering with itself, changing its behavior when we observe it, I am struck by how strange the universe really is at its most fundamental level. But this strangeness is not a defect in our understanding. It is a feature of nature itself. The universe is under no obligation to conform to our expectations or to make sense according to the rules we have derived from everyday experience. The double-slit experiment teaches us humility, teaches us that reality is far more subtle and surprising than we ever imagined. And this, ultimately, is what makes physics so fascinating. We are not just learning facts about nature. We are discovering that nature itself is more wonderful, more mysterious, more profound than any story we could have invented. The most confusing experiment ever is confusing because it opens a door into a realm where our familiar concepts break down, where we must learn to think in new ways, where we must accept that complete understanding might mean something different from what we thought. And passing through that door, embracing that confusion, accepting that strangeness, is the price of admission to the quantum world, the world that underlies everything we see, the world that makes atoms stable and chemistry possible and life itself feasible. The confusion is not a bug. It is a feature, a sign that we are touching something genuinely deep about the nature of reality.